Swayam Prabha. Digital India. Educated India.
So what we have seen in the last class, we'll continue now, take forward the discussion for further building blocks of the microprocessors. So we saw combinational logic, we saw sequential logic, and now we'll see how to build memory using now some of those fundamentals. And further we are going to kind of see the construction of like some primitive microcontroller or microprocessor, so that we understand some basic stuff, and then we'll go ahead with the the modern microcontrollers or microprocessors, discussing that. Okay, so let me switch to the screen. So what we are going to see is building how do we build memory now out of the D flip-flops that we have seen before. Okay, so if you recall, the D flip-flops hold their state as long as the clock input is given to them. So some, or see, this clock input, if it is going it is changed or it is going as a pulse here, then whatever input is available here will be stored in the value, and that value will be available as a Q. Okay, so one kind of a D flip-flop is going to hold one kind of a bit memory. Okay, so we put together such 3 flip-flops, and all of them are having the same this clock signal. Then they form a 3-bit kind of a register. Okay, so this is how, like, you can construct now 3-bit register. Okay, so we have some 3 storage elements, or 1-bit storage elements, and they are all can be controlled by using single kind of a clock input to store some value. Okay, now let's see how this value can be stored and retrieved from this register. Okay, so we have this basic building block in place, but the question is, say if you want to save this number 101, okay, how do we save that? So that number should be available as high voltage, low voltage, and high voltage again on these 3 pins for one flip-flop here, for this first flip-flop 1, second flip-flop 0, and third D flip-flop it should be 1. Okay, if it is available, then when I give this write enable, now this clock signal we are calling it as a WR, or write enable kind of a signal. Okay, so this signal, like, is this kind of a pulse here, then that pulse is going to get this input inside into and store the value inside this D flip-flop, and now that value will be available at this terminal Q also. Okay, so this is how one can save this value in the D flip-flop. So we are now thinking, like, creating this 3-bit register, and from here we want to retrieve the value. The retrieve value means, like, the value will be already available at these Q terminals, but now say we want to use the same data lines to transmit to transfer the value into the register, or take the value out of the register. So how do we do that is what we the next question. Like, see, if the number if you turn off the power that is given to these D flip-flops, then, like, the memory will be lost. Okay, we will not have the same number available when the power comes back. So this is a different kind of like a memory where it is not able to hold the value when the power goes off. Okay, there are some other memories where this feature can be possible. They'll have some kind of a capacitive elements to hold the value, or some other kind of technologies. Okay, we will not get into the details of that, so you can have a look at and, like, get that information. What we are looking at is, like, fundamental principles of construction of memory, and how do we address the memory here now. Okay, so let me turn off these. So let's say if you have this value to be retrieved from the same data bus. Okay, value to be retrieved to the same data bus, and from that same data bus I want to say some other value to store. So I want to use single data bus or data wires which are kind of giving the value to the memory and which are taking the value out of memory. And so for this we need to have this Q and D terminals connected to the data bus. Okay, but now if they are both connected directly to the data bus, that's not going to be, they are shorted. If they are shorted together, then they'll not function well. Okay, the value will be messed up with the feedback, or some kind of other circuit will happen there. So we want to have the control over whether the value is to be stored into the register, or value is taken off the register and given to the data bus. Okay, so that control we can achieve by using some kind of a small element called tri-state gate. Okay, so let's look at what is this tri-state gate. It has 3 states instead of only 2 states. It has third state, which is C here, which is high impedance kind of a state. So we'll not worry about what is that state for now. It is just a state where, like, the input is the output is such that, like, it is into high impedance kind of a level, and that helps in not draining the current. Okay, so if the impedance is low, the current typically will get drained, but now if it is high impedance state, it will not drain the current. Okay, so that is a kind of a state that we have here. So the truth table for this is, now we have this kind of a special gate which is called tri-state gate, which has a input here, and it's controlled by using this output enable kind of a pin, and then it is getting reflected to output F. So in this case, this is a circuit. We don't worry about how this circuit is constructed and why like it is like that, but one can get into details of this. This is kind of a CMOS circuit which will realize this tri-state gate. Okay, which is inverted kind of a tri-state gate, because output enable is 1, input is 0, output is 1. So one can use some kind of a NOT gate here to make sure that, okay, input and output has the same value. Okay, so you can imagine that, okay, this gate is such that this input value will be on the output only when output enable is enabled. Okay, or it is 1. Okay, so this is a gate we'll make use of in this construction now. Okay, so this is constructed in this kind of a fashion. So this we connect this Q to the data bus through this tri-state gate. So whenever we want this value to be available on the data bus, we enable these pins of the tri-state gates, all pins connected together, the way you have this clock inputs connected together. Like that, we will connect all these inputs together, and then when that is enabled, all these data values will be available on respective lines of the data bus. Okay, so this is how I can transmit my data, okay, from a register to a data bus. Okay, now I want to get the data from the data bus to the register. How do I connect? So where this D should be connected? So you might have guessed it right. Okay, pause and think about before you listen to the answer. So yes, the D lines can be directly connected to data bus, because there is no conflict, because unless so lot of this data bus will have a lot of this data which is continuously changing, but that data will not disturb this register, because unless the clock goes high or this input goes high, this D value cannot be stored into the register. Okay, so now we are slowly kind of building up now to see how the data can be controlled in and out of the registers. So this is the same principle now we can extend for getting the 8-bit register created. Okay, so in the very similar way, we can put 8 kind of a D flip-flops together and create 8-bit kind of a register here. Okay, so this has all these clock inputs connected together to this right pin, and all these input to the tri-state gates connected together to the output enable, and you see this data bus is directly connected to the D pin, and the Q is connected through the tri-state gate to the data bus. Okay, this is how your circuit for the 8-bit register would look like. Okay, so now henceforth we'll just look at this. So you can imagine that, see how each of these you know each of these parts can be seen at different scales. Say for example, if 8-bit register is just seen as just kind of a block diagram like that, it has inside this kind of a circuit. Inside each of these D flip-flop, there are this lot of this RS flip-flop and gates and other kind of logic blocks. Each of those logic blocks will have CMOS transistors working at the base. Okay, so like that one can imagine, like, okay, this is getting now scaled up further. Okay, so this is how our computer gets built. Like, it has all these elements that we see at the user level. If you kind of start digging in more details, okay, what is it is at a hardware, you'll find all these kind of features to be there at the hardware level. Okay, so now this we will refer to henceforth this register just as this small little block with output enable pin and WR pin. Okay, this output enable, when it goes high, the data from this 8-bit register will be available to the data bus here, and when write pin is high, then the data from the data bus will be returned to this register. That is what is there. They both cannot be high at the same time, because then, like, if you see, if they both are high, then this data clash will be there. Okay, it's like shorting the Q to the D. Okay, which is like having some kind of a data clash. Okay, so so from here we move on to how do we kind of store the data and retrieve the data. Okay, so if you want to store the data, again, as I said, WR pin needs to get enabled for some finite time with output enable being 0. Okay, so we need to make sure the output enable is 0 and WR is made high for some small pulse kind of is given on the WR pin, and then your data will be stored. Now if you want to transfer the data from the register, okay, now this register to the data bus, we need to enable output enable, and we need to have, of course, WR to be low. Okay, and then the read operation will happen, that we are reading the value from this register, and that is available on the data bus. Now this data can be exchanged between the registers through this data bus. Okay, so now we can think how this can happen. So you have these two registers here. Okay, and this register A and register B, and from here I want to transfer the value to this register. Okay, from register A I want to transfer the data to register B. So from the A I should first transfer this data to the data bus, and from the data bus I should transfer the data to the register B. Okay, so I'll transfer the data from register A to the data bus by using output enable for the A register to be high. Okay, now this data is available here. Now at the same time I need to do this WR to be high for a short duration, then that data will be stored in this register B, and then I can make WR to be low, and now A's data is also there in the register B. So is the data in the A register lost? No, we have not written anything to A register, so that data is still intact there. Okay, so like that this operation is going to happen. Okay, so this is about, like, so we have constructed memory elements. Okay, now we will need to address this memory. So how do we know, like, that, okay, we are at this register or this register? There'll be, like, thousands and millions of registers like this available. Now we need to address this register. Okay, we need to know, okay, which register I want to move the value from. I cannot give this just some arbitrary ABCDs kind of a thing. So we need to have some numbers or addresses given to the registers. Okay, so how do we create that address kind of a feature in the register is what we need to see. So so this is like, we have all these rooms constructed for a hostel. Okay, and students are to live in these hostels, but now we don't know that room numbers are not there yet. Okay, that is a kind of a scenario. So you have this many rooms available, but you don't have address available for those rooms. So we cannot designate, okay, which student is allotted which room for stay. Okay, so to do that, now why this will be required? See, if there are 2-3 rooms, it's very easy, but if there are millions of rooms, like if you want to scale this up to millions of registers, okay, where you have say some megabytes of memory, then this becomes a issue. Okay, so you want to give this address. These addresses are given as a binary numbers. Okay, some binary number is given as address, then I should designate that this goes to this register. Okay, so that means like I need to have some binary number representing when that number happens on some other lines which are called address bus. Then I'm particularly referring to that particular kind of a register. Okay, so how that happens. Okay, so let's see. So let's say we have this n 8-bit registers. A huge memory can be formed like that. Okay, this is random access memory that we have here. Okay, so now to address it, okay, so these are like so many kind of registers connected together, and then this is a 8-bit data line which is available. Why this is 8-bit data line, or why there are 8 lines here? Because this is a 8-bit register. Okay, so this register has 8-bit, one register has 8-bit memory locations. Okay, like that you can have 16-bit data also, we can have 32-bit data also, like that you have that kind of a scaling possibility. Now to address give address to each of these registers. To address that, we need to create some more kind of a logic here. Okay, so say we have a 4 registers. Okay, just for example. Okay, and the addresses are 0001. So there are binary addresses, 4 binary addresses addressing these 4 registers. So we need to select one of them at a time, so to address, or to take a value from that register, to write a value from that register, to write a value to that register. Okay, for that we need to select one at a time. How do we do that? So say that we first create a bus called address bus. Okay, so on address bus we'll get these numbers available. Okay, 00, if 00 is available, I need to address only the first register. Okay, so how to address that? How to address first register? By using this kind of the logic called decoder logic. Okay, so given address, it gives particular line to go high. So this question is, how do we connect now the output of this? Okay, so this is the next question. First, how do we kind of like, what is this logic here? Okay, so this logic will be something of this sort, where you have this address that is available here. Say this is the address line here on which the address is available. When this address gets available, then only one of these 4 pins will go high, and each of these pins will be then used for either write or write or output enable for that particular kind of a register. Okay, so how do we use that is the next question. Okay, but this is a base kind of a requirement where we have the address given, then like one of the pins is going high. So if we have 4 registers, then we need 2 address lines. If we have say 10 registers, think about how many number of these address lines will be required. Okay, so say 4 binary numbers will give us 16-bit kind of a representation. Okay, yeah, so 4 binary, so we can go up to 16 registers. For 16 registers to be addressed, we need 4 data address bits. Okay, so irrespective address and the data bits are irrespective of each other. Say I can have 3-bit data or I can have 8-bit data, but number of registers is important for address. Okay, if I have 10 registers, then that determines what is the address. But if I have say 4 registers now of only 2-bit kind of a memory, I still need this for the 2 lines for addressing. Okay, like that you need to think about. Okay, so the data capacity or data bits in one register is independent of number of registers that I am using and number of address bits that will be required. Okay, all right, so now how do we connect this connection is shown here. So you think about how do we connect this output of the decoder to respective OE and WR pins of registers. Okay, so that we can address them, so that OE and WR cannot be one at the same time, and we are able to address whenever we want to write output, when we read to write, I don't have to kind of I can do it in a simple manner. Okay, so to do that, this is a way it can be connected. You can see that we have put some kind of a AND gates here. Okay, so this AND gate is connected to each of these. One of the pins of AND gates is first these AND gates are connected to both output enable and WR, as a output of the AND gate is connected there, and then inputs are shorted to connect to this decoder, so that now I can address this particular memory location, and depending upon what I write, what I put here, this is now my output enable one single pin. Okay, for all the registers, this one single pin will be there. Okay, so I don't have now, see, if you remember, previously we had multiple pins for this multiple output enable and WR pins. Okay, so now I'm creating some kind of a additional feature to address them independently, and write and read operations are kind of controlled independently. Okay, so you address this register, and then read and write will happen only on this register. Okay, if you address some other registers for this by the same pins output enable and WR, the read and write will happen on different register now. Okay, so this is how one can think about creating these kind of features that we would like to have in the system, so that we can address now the data in each of these registers, and address that particular register, and then get the data out of that register, or write the data into that register. And how do we exchange the data? By using this data bus. Okay, so we'll not worry about what is a decoder logic that is constructed. You can think about that. Okay, I'm skipping these slides for that. Okay, so decoder logic will have some kind of a truth table and expressions are given here. Okay, so typical memory chip will look something of this sort. Okay, in terms of some kind of a architecture kind of a diagram. Okay, it will have, say, address bus, and it will have a data bus, and it will have read or output enable kind of a pin, and it will have a write kind of a pin. Okay, so now we have, say, 4-byte memory. Okay, and this has 8-bit data registers. So then it will have 8 lines for the data, and then 2 address lines. Okay, so because it is a 4-byte kind of a memory. Okay, so like that, if you have larger and larger memory size, you can see how much how long the data bus that you need. Or if you have, say, 8 lines of the address bus, 8 lines of the address bus, then how many maximum number of registers can be there in the memory. Okay, so 8 lines means you can have 256 registers in that memory. Okay, so 8 line address bus, and whatever number of data bits, we don't know, we can have any number of data bits, doesn't matter. Okay, once you fix the address number of address bus lines, then number of registers get fixed in the memory. Okay, so this is a main understanding for this from the memory perspective. Okay, so then there are these different kinds of variants that will be available. Okay, so now the question is, how do we sequence of operation if it is to be carried out? How do we carry out that? Okay, so this is one of the examples. So for writing data from some external register to the specified address location in the memory. Okay, this is the operation that is given. Okay, so what do you think about this? Writing the data from the external register to specified address location in the memory. So you need to place some address on the address bus. What does it mean is that the address bus lines are now 0, 1 according to the address that is needed there. Okay, so physically that is the meaning. Address bus has some lines are at 0 volts, and some lines are at a higher volt. Okay, 5 volts or 3 volts, depend upon what is the voltage level used. Okay, so that will create some kind of a address on the address bus. Now that particular register can be addressed. Then you want to kind of have a data on the data bus coming from the external register. Okay, so this so you select this chip. So there are some additional features that will be there, where there are multiple chips that are there, and you want to select one of the chips. Then you can select this chip for the operation to be done. Then this this write enable, okay, is there. Okay, so you place bring this also to low. That means like you enable the write operation. So you can have these 3 and 4 can be interchanged also. Okay, you can place the data from the external register on the data bus, and then this bring it to low, and then bring it to high again. That is one possibility. Or you can have this, so basically 3 and 4 can exchange with each other. Okay, so and then this write enable is again closed or disabled. That means the data is now in the memory. Okay, so from external register it is now locked into the that particular address location in the memory. Okay, so this is a kind of one of the sequences of operation that can happen. Like that, one can think of many different kind of possibilities for like doing some kind of say you want to move the data from one of the memory locations to other memory location. What is the operation? Like that, one can start thinking about different sequences of these operations that can be possible. And when you start writing your program, or that program gets executed, this is what happens at the hardware level. Okay, how does it happen? We don't worry about that right now. Okay, we'll see some glimpses of it in the next class maybe. But right now you see that okay, these kind of operations can be performed. Different kinds of operation sequence of operations can be performed by using this steps for executing that into your system. Okay, and the basic thinking philosophy here is this, so this helps us to develop our understanding about how things could be happening at a base hardware level. Okay, so again, I'm giving you some kind of a thing that okay, this understanding is not really a must kind of a thing for you to start programming microcontroller. Okay, anyway we are programming our microprocessors, computers programming. This is not really necessary, but if you have this understanding, this will help you think better in terms of your programming. Okay, so that's why we are going through this little bit more details about how things happen at the hardware level. Okay, so now let us see this entire thing can be represented in terms of some kind of a timing diagram. Okay, so this timing diagram is given like this. So this address bus is given as we are not now using it as each line what is a value and things like that. We are just representing entire address bus as a one kind of a signal, where from this point in time to this point in time 1 to 8 kind of numbers or steps of the time that are given. All the time this valid address is there on the address bus. Then this chip select will go low, chip select bar will go low. That means chip select will be happening here in this domain. Okay, say this write enable is happening here in this domain, and the data becomes available. Valid data will become available from this 4 to 7 or from this time, okay, duration here. So these numbers are written as say different kinds of a step that is going to happen. So first step you'll have this in time happening, then second in time happening, third in time happening, then you'll have valid data available when you have this external register output enable is enabled on that, and then that data will be taken off that register. But before that you'll have the WE going high. That means the data is kind of locked. So otherwise what will happen is, if this is still low and some data is changed here, or some invalid data comes, this is some kind of invalid data in this domain comes there, and still this operation is not completed yet, okay, then that data may get stored in that particular address instead of whatever valid data that we wanted to store. Okay, so this is how, like, typically the timing diagrams are given, and our ability to read these timing diagrams is important. How do we think? We think, okay, of first what are the inputs and what are the outputs. Okay, so here, like, for example, this output enable is an input given to this external register, and as a result of this, what is happening on the data bus is this. Okay, so like that, this is input, this is output. Then you need to see, okay, this chip select and this address bus, these all are inputs only. Okay, so this is what we are giving as inputs, and only, like, whatever is available on the data bus is output, because that we are assuming that data bus is connected to the external register, and when external register is made output enable high, then the valid data is available on the data bus. Okay, so like this, these are through these operations, this data from the external register is getting transferred to this whatever address that you have addressed, put in on the address bus, that particular address of the memory, this data will get transferred to that particular register. Okay, so these are the operations that are happening as they are supposed to happen if you want to transfer the data. Now, how do we make this happen? Is for this you need a timing circuitry or timing diagram, okay, or timing additional kind of a timing inputs. Okay, so how do we do that? We'll see it in the next class, along with some of the primitive kind of a microprocessor constructed, so that you can get a glimpse of how this whole thing are like such a nice kind of a way they are interconnected and made to function to get us the functionality that we want as a user of microprocessor or microcontroller. Okay, so we'll see that in the next class, and we'll not get into too many details about how things happen, but these are the base kind of elements that we are putting together to just see, okay, this based on these elements, now your entire microprocessor architecture and all the interfaces are built based on this kind of a basic kind of a building blocks or components. Okay, so to just give you this glimpse, although this is not completely necessary for us to program or understand mechatronics, if this is understood, we are very well equipped to do the job in the different scenarios. Okay, so we'll stop here and we'll move on to the next class. Okay.